All right, let's go ahead and start our discussion on rate laws and reaction orders. Before we get going into that, here are the rates of decompositions and formations for the reactants and products of the example we did last time. Please notice that for the rates of decompositions that they're negative because the concentration is decreasing for the reactants, and that for the products these rates are positive because the concentration is increasing. All right, so now the rate laws are going to be different from the general rate expressions that we just dealt with. So for a rate law, let's go ahead and look at this general example. A plus B goes on to form products. If you were writing the rate expression, you would use the coefficients. Okay, but whenever we start to write the rate law is an expression that relates the rate of the reaction to the rate constant and then the concentration of the reactants. So what that means is you're going to have an expression like this, where we say rate is equal to K, the rate constant, times the concentration of A to the X times B to the Y. Well, how do we get those exponents? Well, we aren't going to get those exponents from the coefficients, okay? So the coefficients in general will not be the same as the exponents. If they are, it's just by coincidence. So just because you have a reaction that says 2A plus B yields products, you can't write the rate law as this. You can't say, well, judging by the coefficients, it would be this. The rate is equal to the rate constant times A squared times B. That would be incorrect. Well, how are you going to go through and determine what those exponents are? How are you going to figure out what X and Y are? Well, you can't look at the coefficients, so we're going to determine those from experimental data. What we should see is they're going to be small positive integers. We can also calculate the rate constant, that proportionality constant, from the experimental data as well. After you've gone through and found what X and Y are, what your exponents are, you can actually figure out the reaction order. The reaction order is going to be the sum of your exponents, and we're going to go through and explore the effect on reaction order, on the effect of rate here in just a little bit, and then as we get going, we'll also be able to use different reaction order equations to find the concentration at a given point in time of our reaction. So let's go ahead and look at our first example here. So for this rate law, we have the rate is equal to the proportionality constant. So there our rate constant times the concentration of A squared times the concentration of B to the first times the concentration of C to the 0th. So for convenience, what you want to do is you want to go through and assume that the initial rate is 1, the rate constant is 1, and that all of these concentrations were 1. Because we're looking for a relative change. And this will just simplify things. Okay, so what happens to the rate whenever A is doubled? Well, if we're going to compare it to the initial rate, we can plug in, so we have rate is equal to K times, well now instead of being 1, A is now 2. So we'd have 2 squared times 1 times 1 to the 0th. So the effect of doubling A would end up making this rate 4 times as much. So the rate would increase by a factor of 4. Okay, well, what happens whenever we go through and we double the rate of B? Well, here we plug back in and we see that the overall rate is doubled. And then finally, whenever we look at C, if we double the concentration of C, then we return B back to 1, we're going to see that because c is to the 0th order, that there is no change to the rate, because anything to the 0th is 1. Let's go ahead and pause the video and then try to figure out what happens to the rate when a is halved, b is halved, and c is halved. All right, so what we should see is that the concentration of A, whenever it is halved, the rate goes to 1/4 its initial value. When the concentration of B is halved, the rate goes to 1/2 the initial value. And whenever C is halved, there is no change. Okay, so what is the overall reaction order? Well, it's second order with respect to A, it's first order with respect to B, and 0th order with respect to C. So we're just going to go through and take the sum of the exponents. So we'll have 2 plus 1 plus 0, so the overall reaction order is 3. Let's go ahead and try to figure out how we can solve for these exponents. So as we look at this example here, this is a set of experimental data for the reaction of nitrogen monoxide with oxygen to yield nitrogen dioxide. How are we going to go through and find what our exponents are? So think about what the general form of this rate law would look like. So we would have rate equals K times the concentration of NO to the X times O2 to the Y. All right, so right now whenever we look at this expression, well, we know a rate, we know the concentration for any of these trials of both NO and O2, but then we run into a fairly significant problem as far as algebra is concerned. We have one equation, but we have 3 unknowns. So we can't solve this equation. So what we need to do is we're going to need to compare a couple of the rates together to try to eliminate some of these terms with the unknown. So what you're going to want to do is you're going to want to compare things where the concentration is staying the same. So you might want to compare rate 1 with rate 3. Okay? So we would have rate 3 over rate 1. And then we could plug all of this in. So we'd have K times, and then the concentration of NO is 0.015 to the X times O2, which is 0.030 to the Y, divided by K from rate 1. Whoops. All right, so we have this expression here. So what this allows us to do, and we can go ahead and plug in these rates over here as well. So we'd have 0.096 molar over 0.048 molar. And whenever you're setting these up, it tends to be easier if you put the larger rate and the larger concentrations on top. Okay, so for this rate law, what we're going to see is that the rate constants, it should be a constant, so that should cancel out. So there's one of our unknowns gone. Okay, well, we still have the X and Y terms. Well, 0.015 to the X divided by 0.015 to the X goes to 1. So this term goes away. So now we can simplify this expression right here. So 0.096 molar divided by 0.048 molar, that goes to 2. And then this expression here, 0.030 divided by 0.015, and both of those are raised to the y, we can rewrite that as 2 to the y. So that means that y has to be 1. Okay, we can go through and we'll discuss the law of logarithms in class. All right, so we just found our exponent for oxygen. Okay, we just found what y is. So now we need to compare two trials that will enable us to find what x is. So what two trials should we compare where now we're holding oxygen constant? Well, I would go ahead and compare trial 1 and trial 2. So let's go ahead and work this out on the next page. So for this one, you'll want to put rate 2 on top because it is larger than rate 1. So we'll have rate 2 over rate 1. Plug in those values. And then plug in your rate law. So again, we have K times 0.030 molar for the nitrogen dioxide, and that's raised to the X, times the concentration of oxygen, 0.015. But instead of raising this to the Y, we already calculated what Y is, so we can plug it in as 1. And we'll have K so that's from rate 1, so that's 0.015 molar to the X times 0.015 molar to the 1. So let's see what we can simplify. So 0.192 divided by 0.048, this is equal to 4, equals, K's cancel out, it's a rate constant. This expression will cancel out the 0.015 molar to the first. And then we can simplify 0.030 divided by 0.015. So that will end up being 2 to the X. So what this means is X is equal to 2. So we can write our rate law. The rate law is equal to the rate constant times the concentration of NO squared, that's what X is, times the concentration of O2. We don't put the 1 because it's implied. Okay, so now we found the rate law. We found that overall this reaction is third order. So the last thing we have to do is to go ahead and go through and calculate the rate constant. So to calculate the rate constant, you just pick your data from one of the trials and you plug it in. So let's go ahead and use trial 1. So you plug in your rate, 0.048 molarity per second is equal to K times the concentration, 0.015 molar squared of NO times the concentration of oxygen. Then upon solving for K, you get 1.4 times 10 to the 4th per molarity squared times second. So those units might seem a little strange, but all of these units on the rate constants differ between the orders because you're always going to have different coefficient values, okay? So let's go ahead and take a look at that. We know that the rate is always going to have units of molarity per second. We said that this is the change in concentration over the change in time. But depending on the order, your rate constant will have different units. So if you have a reaction that is 0th order, so if we have rate is equal to K times A to the 0th, well, this term really goes away. If this has units of molarity per second, that means K also has units of molarity per second. Well, what happens if you have a first order reaction? Well, here we have rate is equal to K times the concentration of A. Well, if rate again has units of molarity per second, concentrations in molarity, that means the units for K has to be 1/second. So you can tell the order of the reaction by just looking at the units of K. What you'll see here is the trend is every time your order increases, so from 0 to 1, first to second, second to third, you're just dividing by molarity. So you can recognize the order of the reaction by the units of K. All right, so here is the last example. I would like you to go through and find the rate law. So that means solve for your exponents, x and y. Then find the value of the rate constant, k. And then once you have your overall rate law, go through and plug in these initial conditions and find what the resulting rate is. So you can go ahead and pause it, and then I will call up the slide with the solutions for you. All right, so that will do it for now. Just remember, smash that like button.